In this video, we are going to perform the Bradfoard protein assay to determine the specific concentration in all collected fractions from the isolation procedure. Bradfoard assays are Kumasi dye binding assays. The assay is performed at room temperature, standard, and samples are added to pre-formulated Kumasi Blue G250 assay reagent, and the resultant blue color is measured at 595 nanometers. Before starting the experiment, we must wear gloves. The first steps to perform serial dilutions for BSA and lysozyme solutions. We took 10 microcentrifuge tubes for BSA dilutions and 10 for lysozyme. As you can see in the photo, we have labeled the tubes with concentration starting from 1 mg per milliliter to 0.002 mg per milliliter. By using a 200 microliter micropipette, take 200 microliters of BSA stock solution into a microcentrifuge tube labeled BSA 1 mg per milliliter. In all the other 9 tubes, take 100 microliters of distilled water using the same micropipette. Make sure to always work at an eye level. Now take out 100 microliters from 1 mg per milliliter tube of BSA solution and add into the tube labeled 0.5 mg per milliliter, which already contains 100 microliters of distilled water. Slowly pipette up and down to mix the solution. Close the lid and then vortex. Repeat the process until you reach 0.002 mg per milliliter concentration. For each step, we have always used a new pipette tip. Our sample has 5 mg of lysozyme. By using this formula, we can find out how much lysozyme we need to prepare 1 mg per milliliter of lysozyme solution. We want 1 mg per milliliter of lysozyme concentration, but we have 5 mg per milliliter, which is why concentration wanted is 1 mg per milliliter and concentration given 5 mg per milliliter. And the total volume that we want at the end is 200 microliters. To prepare 1 mg per milliliter of lysozyme solution, take 40 microliters of lysozyme and 160 microliters of water using 200 microliter micropipette. Close the lid and vortex. In all the other 9 tubes, take 100 microliters of distilled water. Now take out 100 microliters from 1 mg per milliliter tube of lysozyme solution and add into the tube labeled 0.5 mg per milliliter. Repeat the steps for each dilution. Serial dilution steps are the same for both BSA and lysozyme solutions. For each isolated protein sample, F0 to F4, dilutions prepared in duplicates. Add 490 microliters of water and 10 microliters of sample in both F0s. Slowly pipette up and down, then vortex. Take the same amount of water and sample for F1. For F2, 250 microliters of sample and 250 microliters of water should be taken. For F3, dilution is not required. And lastly, take 50 microliters of sample and 450 microliters of water for F4. All tubes should be vortexed and the total volume in each centrifuge tubes should be 500 microliters after diluting. Now it is time to use the Bradfoard reagent. To measure the absorbance of all samples and the serial dilution, a 96 well plate is used. add 90 microliters of Bradfoard reagent to each of the 11 wells of the first row and 10 wells in the second row. Starting from 1 microgram per milliliter of BSA solution, 10 microliters of each serial dilution of BSA is added to the first 10 wells. The 11th well is filled with 10 microliters of water and considered a blank. As you can see in the video, we have vortex each tube before plating. In the second row, add 10 microliters of the samples with unknown protein concentration, F0 to F4. Mix the content gently by pipetting up and down. To avoid bubbles in all wells, always stop at the first stop while pipetting. If you stop at the second stop, numerous bubbles will be formed, which will have an impact on the OD measurement. Leave the third row empty. Fill the 11 wells of the fourth row, 10 wells of the fifth row, and 11 wells of the sixth row with 200 microliters of Bradfoard reagent. We are going to follow the same steps as before, but this time add 50 microliters of each serial dilution of BSA solution to the first 10 wells of the fourth row, 50 microliters from F0 to F4 in the fifth row, and 50 microliters of each serial dilution of lysozyme solution to the first 10 wells of the sixth row. As I mentioned before, vortex before pipetting. 11th well of the fourth and sixth row are blanks, so add 50 microliters of water. So in total you will have 3 blanks. To measure the OD, we are using a spectrophotometer. Open the lid of the 96 well plate and place it inside the spectrophotometer and run the software. The absorbance can be read at 595 nanometers. Wait for a while until all the measurements are shown on the computer. Save the data to make a standard curve later. This is the time to learn how to work with the data on Excel. The data that you can see are generated by the spectrophotometer. We are going to use these to make a standard curve. This part gives us information about the concentration and name of each sample and solutions with dilutions. The OD measurements are colored in pink and yellow. Here shows the amount of Bradfoard reagent and sample used in each well for OD measurement. These are the BSA concentrations according to the script, which has also been shown in the previous video. Concentrations starting from 0.1 mg per milliliter will be used in this video so that you can use the other values to practice at home. I'm going to use these values to make the standard curve. These are the blanks. We are going to take the mean value of these two blanks as they have the same concentration. To calculate the mean value, type equal, average, open bracket, select the first value, semicolon, select the second value, close the bracket, then press enter. Now we have to subtract the mean value from all the OD values of BSA. To do that, type equal, select the OD value of BSA, minus, select the mean blank, then press enter. Do the same for all the other OD values. To plot the curve, make sure that the BSA concentrations are on the x-axis and OD measurements are on the y-axis. Now select these values, go to Insert, click on Charts, and choose the first scatter plot. Label y and x-axes with units. Single click on the plot to get these options. Click on the plus sign named Chart Elements, then choose Trend Line. You can see there is a line through the dots. To get the equation, make sure to select Display Equation on Chart. The equation tells us the slope, which is 3.9812, and the y-intercept 0.0663. To find the concentration of our samples F0 and F4, we need to solve the equation for x. Since each isolated protein sample, F0 to F4, dilutions were prepared in duplicates, we can take the mean value unless there were too many bubbles in one of the wells. Now take away the mean blank from mean F0 and mean F4. Type equal, open bracket, select the mean F0, minus, select the mean blank, close bracket, then press enter. Do the same for F4. To find the concentration of protein in F0 and F4, we are going to use the formula x equals to y minus 0.0663 divided by 3.9812. Type equal, open bracket, select the mean value without the blank of F0, minus, select y-intercept, close bracket, divide by the slope. Do the same for F4. Before measuring the OD, F0 was diluted by 50-fold and F4 was diluted by 10-fold. So multiply 0.1625 mg per milliliter with 50 and 0.0442 with 10. When the egg white was prepared at the beginning, we diluted it by 6-fold. Therefore, we have to multiply 8.17 mg per milliliter and 0.44 mg per milliliter with 6 to get the initial concentration of the entire protein content and lysozyme. Please use Table 15 of Unit 5 to compare experimental data with the literature value. The weight of the egg was 55 grams and the content of the whole egg is 100%. Only 60% of the entire egg is egg white. The protein content of the entire egg white is 11%, and only 3.4% of the entire protein content is lysozyme. The total protein content possible is 120 mg per milliliter, whereas experimentally we got 48.7 mg per milliliter. 4.2 mg per milliliter of lysozyme is possible, whereas we've only managed to obtain 2.655 mg per milliliter. We can definitely see a huge difference between these values. If F0 is considered as 100%, then 3.4% of that is lysozyme, which should be around 1.66 mg per milliliter. Since lysozyme concentration in F4 can't be more than the concentration in F0, we can assume that there were some dilution errors or the isolated protein was in the freezer for too long, that some protein may have been destroyed. Can you think of any other reasons?